Okay, part two, we're going to look at this conversion thing. So we can go both polar to rectangular, so we should also be able to go rectangular to polar. So just like we can convert from feet to meters, we can convert from meters to feet. It's just a different way of looking at things. It all comes from this picture, which is really, really easy to create. So these could be some good test questions, extra credit type stuff, whatnot. Put a little smiley face there, there's a point. Okay, so it's x comma y. We went over 10, we went up 7, whatever it is. Okay, easy enough. If we're in polar now, we don't say over 10 up 7, we say it went some angle, we don't know what it is, in some radius. Well, if we know the x is 10, we know the y is 7, simple Pythagorean theorem gives us that. If we want some equations we're going to use to convert between these two, all we have to do is find this picture here and go, okay, how do I relate x and y in theta? Well, I do it in two different pieces. I would say cosine of theta is the exact same thing as adjacent over hypotenuse, not a y. How about an r? So therefore, x equals r cosine theta. You don't want the r after the theta because you don't want to group it in there with it. Same way here. Sine of whatever this guy is, y over an r. So one thing I'd like you guys to get out of this course is kind of how we build this whole different system based off simple little pictures and right triangles. Okay, and the more you do this, and obviously I've taught it a lot and worked on it, but you see connections and things start to look really cool. Okay, there's your two things right there. That's all you need to convert from polar to rectangular. Here's your questions. Find the rectangular coordinates of the points with the following polar coordinates. So I'm giving you polar. I'm asking you to go to rectangular. Okay, we just came up with two formulas. That's all you need right there. Okay, I'm going to do A with you, and you guys can see the answer for part B there. I'm going to have you guys try that there in your notes. So this is definitely a polar because I see a r and I see a theta. All I have to do with those, go plug theta in and theta in, go plug an r in and an r in right there, and I'll have it. Now, I don't want you guys to grab for your calculators here. We know what pi over 3 is. Okay, obviously that's 60 degrees, so we'll just throw that in here. So cosine of 60 degrees is 1/2. Sine of 60 degrees is the square root of 3 over 2. Okay, and notice how I wrote the answers. You can say 2.5. Typically, you're going to see it as improper fraction here. So I wrote it as an x comma y because that's how you guys would see them in rectangular. Here's the r and a theta. I transformed it. All I had to do was plug in the same thing twice and just evaluate. So it's a simple little conversion. So you guys go ahead, try B and see if you can get this x in this y. Okay, it's the exact same idea. Now, we want to go rectangular to polar. So using the rectangular stuff, how can we relate some polar things around there? The only thing I have is an x, y, r, and a theta. Okay, so I'm going to do this. There's one thing I definitely know from that picture, because we know in rectangular, that makes a 90-degree angle. The only other thing I know then is tangent of theta is y over x. No, I don't want to use that r because I want to go rectangular to polar, meaning I was given the y, I was given the x. Can I transform it into polar? So these are our two equations we're going to need going the other way. Just make sure your notes are nice and clear that when you're going rectangular to polar, you use these. Now, these steps here, if you want to copy them down because they'll help you, great, do that. This way is a little bit more difficult than going polar to rectangular. Okay, so first step we say always plot the xy first. To find r, compute the distance from the origin to xy. That's pretty easy. That's just a simple Pythagorean theorem coming right from this guy right here. Step 3 is where it gets a little bit tricky. To find theta, first find the quadrant that the point lies in, and then do this. So quadrant 1, we don't have to worry about it. Quadrant 2, you're going to add a pi to your answer. Quadrant, this should be a 3. Okay, quadrant 3, you're also going to add a pi. In quadrant 4, we're just going to leave it alone. If you understand why we're doing this, great. Okay, but like with a lot of things, I teach you guys the understanding behind it, and you don't have to worry about the memorization with this. Okay, so let's look at one last example here. Find the polar coordinates of a point whose rectangular coordinates lie at -3, 4. So when I see this, clearly 4 isn't an angle, so I know this is an xy. So I'm trying to go rectangular to polar. The only things I have are this. Okay, finding r clearly isn't hard. Make sure you get it in the appropriate quadrant here, like this little picture. I'm not going to show you guys the math there. Simple Pythagorean theorem, done. Okay, r is 5. So there's one thing. Now, we got to get that theta somehow. So we got to go use this equation over here. So if I say tangent of theta equals, and ignore these labels here. I don't like those labels. Those are going to get us confused. Okay? Tangent of theta is y over x. So go to this triangle here, how I taught you guys all year. We know this is -3. We know this is 4. Let's call this one theta, because that's what we really care about. So this is opposite over adjacent here. So you grab your calculator. We're doing radius comma thetas. Okay, so we're not doing degrees anymore. So the biggest thing is go change your calculator back from every place you were in chapter 7. So I'm in radians. Spits out -0.927 at me. So when we think about why that is, well, what are tangents in quadrant 3? Tangents in quadrant 3 are negative. Okay, so basically it's saying this little angle here is 0.927 radians. The only reason it's negative is because it is in quadrant 3, and we tried to do a tangent of a negative, so it can happen in 2 different places. Now, that's what we want, that's what we care about. But this is actually the angle that we need to use to represent this. So how far did it take to get from there to there? Let's call that guy theta 2. So we may have to go briefly to a part 3, just because I don't want this to go longer than 10 minutes and not be able to upload. So see you in part 3 for a couple minutes.